Before we start talking about our project, I would like to give a very brief introduction about our company because it's might related to the project that I'm going to say today. So SCG, we are the cement producer in Thailand, and we was founded in year 1913. So we are a 109 years old company, and we are the second largest conglomerate in Thailand. And in year of the 2 years ago, we had the initiative by the top management to build a memorial courtyard of the founder of our conglomerate SCG. This is a King Rama VI, as you can see on the left-hand side. And also we have got the approval to construct a bridge to crossing from the parking lot that you not see in the picture on the right-hand side toward the memorial park, toward the statue of King Rama VI. And if you see the dimension, everything is not very big space. You want to cross over the pond about 30 meters span length. And the distance between the abutment to the monument is like a 30 meter. And of course, in Thailand, I'm not sure in anywhere else, in Thailand, we love the arch bridge. So when we construct the pedestrian bridge, it has to be arch bridge. And but one requirement from the top management and the architect of the company is about the height, because we want to, when the people cross over the bridge and we stand at the midspan and look toward to the monument, to the statue, it should have a kind of the perfect altitude to make the statue look magnificent. So what we did at the moment, so we had the platform on the water, and the architect team, they just stack blocks and stand on that and try to look for the perfect altitude that make the statue look very great. And eventually they finished with a number that the height of the midspan has to be 1.25 meter, not more than that, because they want the altitude angle to the monument. Okay, and this is the requirement of the architect. Is on the right-hand side, you can see the aerial view of the monument and the bridge. And you can imagine when we cross, we should see the courtyard and the monument in the most perfect point of view. And yeah, as people always say, that the architect dream is always engineer nightmare, because we know that when we build the arch bridge, it should have a proper ratio between the height and the span. So if we talk about the golden ratio of the arch is like a 1:6, but in our case, because the span length is about 28 meter, the number is wrong, I'm sorry, and the height is 1.25 meter only. So the ratio between the span to the height is like a 22:1. So what happened when the arch bridge is flat, is create a lot of the lateral forces. That can you see on the vector on the left and right hand side. You can see that in case of the lower one, when you have the flat arch bridge, it create a lot of lateral forces to the foundation, and we need only little force for the data of the structure. And when we do design this way, we need a big foundation. So we spend like 3 to 4 months to solve this problem. We thought about use the batter pie or the barrage pie to reduce the lateral forces of the structure. And it is very expensive foundation work for the barrage pie. We think the budget is more than like 60% of the total budget that we got for the whole project. And after we think about it, so we end up with the engineer design of the engineer team. We think that why don't we just simply cut the beam into 2 pieces, and we just stressing each beam to both abutment. So it means we change from the arch bridge into 2 cantilever beams. And by doing this way, we can eliminate the lateral forces. And one thing that as engineer we know, when we decide to cantilever, the tip of the beam, we have 0 bending moment. This means we can reduce the depth of the midspan as low as we can. And in this case, we can reduce to like 30 centimeter of the thickness. Another thing, for the cantilever beam, it has very high bending moment at the support. And we know that when we let the water into the pond, most of the beam will be submerged in the water. So eventually we can get very thin beam all through the length of the beam. So that's the concept of the design. And this is show the beam. So you see it's not the flat, it's a curved beam. And we eventually stressing to the abutment by using the post-tensioning. And once we install the beam, we attach the deck that's also made from the UHPC concrete on the top by using the bolt and nut system. But to achieve this high strength, because we need to put a lot of stressing of the tendon, we have to design the UHPC concrete. We have the foldability. We control the diameter of the flow more than 700 millimeter and try to minimize the viscosity that we use the control value of 7 seconds. And the composite strength for the material is 165 megapascal, but we use 150 for the design. And because for the deck slab, we do not put any reinforcement, and for the beam, it's only the tendon, but no shear rebar. So we want to make sure that it's the strain hardening. That's why we have to put the fiber, in our case, it's 2% to gain the strain hardening property with the tensile strength about 20 megapascal the first crack. Okay, this is show the overview of the process. So we start from the casting work in our ready-mix concrete headquarter. And you can see that because the beam is curved, so we need the formwork that have to be closed in every dimension. We have to pour the concrete into the box, and we have 2 sets of formwork. And when we finish casting, we deliver beam to the headquarter in the Bangkok area, Bangkok. And because the beam can be approached into only one side from the parking lots, so we need to have the temporary support and just sliding the beam one by one into the place. And after that, we cast the top of the abutment. And on the left, the lower left one is a post-tensioning work. That is very important stage, is a moment of truth, because we have to stress in the beam individual. For the first one, it's okay, not difficult. But for the second one, we just make a wish that it would come to the same level, because we cannot do anything, on that day. We just hope that it should come to the same level. Eventually, we can get very good the level. It's only like a 3 millimeter difference. So we're happy with that. And after that, we remove the support and install the deck. I show you this video clip to you because the beam is very slender. You can see it's shaking. It's like 2 springboard. And after that, we connect this beam with a steel frame that design the plate with the slot and the bolt nut. The purpose is to transfer only vertical forces, but not horizontal forces. And eventually, we do the topping and tiling and handrail, everything. And we also install the IoT system. We have the accelerometer attached to the beam on the purpose to measure the vibration. This is data that we collect. We measure the vibration, and we use the fast rate transform to analyze the fundamental frequency and check the stiffness of the beam over the time, whether it's still stiff or not. Okay, so I end with the presentation to show you. Last, I would like to thank the team member. We are from SCG and CPAC, but we also thank Case, who is our structural designer, and China Engineering, who is the general contractor of this project.